Hello there. Welcome back to the Math 22 tutorial series. Today we're going to be discussing motion in space. If you've taken Physics 71 at some point in the past, or if you are taking Physics 71 currently, some of these concepts may seem a bit familiar to you. This is a more mathematical way, so to speak, of viewing concepts such as displacement, velocity, and acceleration. So once again, let's go over some key concepts before we start. So first off, let's view how motion in space works. Suppose an object moves in space and that's position at any time t is given by its position function r of t. Now, this function is going to give us a vector that will tell us what the position of the object at any given time is. So, with r of t now being defined, we can do stuff with it. We can get the distance and displacement of the object that's traveling. So if the object moves from times t equals a to t equals b, from one point in time to another point in time, then the distance that the object has traveled is given by s equals the integral from a to b of the magnitude of our position function with respect to time. Our displacement is simply just the position function evaluated at b minus the position function evaluated at a. So, once again, if you're unclear what the distance and displacement distinguishment is, the difference between the two, it's just that displacement is how far you are from your original starting point. So you look at where you are at point B, and then you compare that to where you are at point A. And your displacement is what's the shortest possible line from point B to point A. Distance, on the other hand, is dependent on the path you took to get there. So if you take a bunch of twists and turns from point B to point A, or point A to point B rather, your distance traveled is going to be longer than if you just took a straight line. And it's reflected here in this integral. This integral tells us that we want to find the length of the total path we've taken from points A to point B, as opposed to displacement where we just want to find the fastest possible path, the distance between the 2 points. You may have heard before that velocity is just the derivative of displacement, and you would be right. Our instantaneous velocity, how fast and in what direction your object is moving, is just straight up given by the derivative of your position function. We also have two other things here, as you can see, the speed and the acceleration, and it's important to distinguish speed and velocity. Well, velocity is a vector quantity, as in it has both a magnitude and a direction. Speed, as you can see over there by the small v not having an arrow on top of it, is a scalar function, which means it only has a magnitude. In that sense, we're taking the magnitude exclusively of the vector function r prime t. We're taking the magnitude of velocity here, and that's the difference between the two. While speed is only concerned with how fast you're going, velocity is concerned with how fast you're going and where. And after that, we have acceleration. Now, acceleration is simply how fast your velocity is changing, and this rate of change we can express as a derivative again of velocity. Now, note that velocity itself is already the derivative of your position function, right? So what's amount to? Well, this tells us that acceleration we can get by taking the derivative twice of the position function. So you have your position function, you take the derivative once, you have velocity. You have your velocity function, you take the derivative again, you get acceleration. Now keep in mind that these quantities are instantaneous, as you can see over here. Now, what instantaneous means is that they are the speed, velocity, and acceleration of this moving object at an instant point in time. You're not taking the average speed or velocity or acceleration across the whole trip. This concerns ourselves with what it's doing at any specific point, an instantaneous point in time, rather than over an average period of time. It's just one point. Let's move on to acceleration. And we can see here that we have two components to acceleration: the scalar tangential component and the scalar normal component. Now they're called these because the tangential component is a measure of the magnitude of our acceleration in the direction of our velocity vector, whereas the normal component is perpendicular to our velocity vector. It measures how strong our acceleration is perpendicular to it. And just as we can see over here, we can get our tangential component by getting the dot product of the velocity and the acceleration vectors and dividing all of that by the magnitude of the velocity vectors. And for our normal component, we can get this one by taking the cross product of the velocity and acceleration vectors, taking its magnitude, and then dividing all of that by the magnitude of the velocity component. You can remember that the scalar, tangential, and normal components measure how strong acceleration is relative to velocity, which is why we're dividing stuff by the magnitude of the velocity vector. Let's move on now. Some sample problems. We have 3 in total. Now, the first one is this one. A dust particle moving through air has an initial position of 0, -4, 2, and a velocity of v of t equals 3t squared, t minus 2 cubed, and 2 times t minus 1 for any time t greater than or equal to 0. And we want to find the particle's position function. Let's look at what we have already. We have the velocity of our dust particle, and then we have the initial position of our dust particle. This will come in handy later. But for now, do you remember how I told you that the velocity vector was just the derivative of the position vector? So if we have the velocity function, how are we going to get the position function? We're going to have to undo that derivative somehow, right? And we can undo the derivative because we can just integrate the velocity function like so. And now that we have this, we can just evaluate this integral. For our x component, we evaluate the integral of 3t squared, and we get t cubed plus constant 1. For our y term, t minus 2 cubed, we just evaluate the integral here, and we get 1/4 of t minus 2 to the power of 4 plus constant number 2. And lastly, for a z component, we have 2 times t minus 1, and we just integrate that as well, getting us t minus 1 squared plus constant 3. And we still have these constant terms, right? Because we have these constant terms, we can't get like the exact value of this integral, right? But we can, because we have the initial position. And so, using this initial position, we can evaluate the function at r equals 0 to get constant 1, 4 plus constant 2, and 1 plus constant 3. And because we know that the initial position is basically just what happens when you evaluate the function at r equals 0, we know that whatever we got from evaluating the result of this integral at 0 is going to be equal to 0, -4, 2. So we have c1 equals 0, 4 plus c2 equals -4, which basically means c2 equals -8, and 1 plus c3 equals 2, which means that c3 equals 1. Now that we have these initial constraints, we can move on to say that, all in all, we have these to plug in back to the integral. And so we have our position function being t cubed, 1/4 t minus 2 to the power of 4 minus 8, because constant 2 is -8, and t minus 1 squared plus 1, because constant 3 is 1. Let's move on to our second problem. A kite follows a trajectory given by v of t equals 4t, 2 times the square root of 2 times t, and t, for t between 2 to 4 inclusive. Find the distance the kite travels during this time period. So, like before, we have our velocity function, and we want something to do with distance. Just like before, we're also going to have to do something with integration. So let's do that really quick. In order to get the distance the kite travels, we're going to need to have the definite integral from 2 to 4 of the magnitude of our velocity function with respect to time. So let's get the magnitude of our velocity function first. We're going to have the square root of 4t squared plus 2 times the square root of 2t all squared plus t squared, which gives us the square root of 16t squared plus 8t squared plus t squared. All in all, that gives us the square root of 25t squared, which is just 5t. Evaluate that. So we evaluate the integral of 5t from 2 to 4, and we get 5/2 t squared from t equals 2 to t equals 4. Let's continue on, and we can evaluate this further. This is going to give us 5 times 16/2 minus 5 times 4/2, which is just 80/2 minus 20/2, which is 40 minus 10, which gives us 30. And so we have a solution of 30 units. Okay, now let's move on to our third problem. This one is split up into 2 parts, so we're going to be tackling them one by one. The floating dandelion seed's velocity starting from a time t equals 0 is given by v of t equals sine t, cosine t, negative e to the power of negative t. Our first part is to calculate the seed's acceleration at any time, and our second part is to calculate the tangential and normal components of the seed's acceleration. Let's start with the first part. This one's the much easier part, because we know that acceleration is simply the derivative of velocity. All we need to do here is differentiate the velocity function, and so we can do that right now. The derivative of sine t is cosine t. The derivative of cosine t is negative sine t. And the derivative of negative e to the power of negative t is simply e to the power of negative t. And so, we get our acceleration right there off the bat. Our acceleration function is given by cosine t, negative sine t, e to the power of negative t. Okay, that's part A. Now let's move on to problem B. Calculate the tangential and the normal components of the seed's acceleration. If you remember the equations to get the tangential and normal components of acceleration, you'll notice that they both had something to do with the magnitude of the velocity function. So that's the first thing we're going to find. Let's get the magnitude of this velocity function. And we can get that by doing the square root of sine squared t plus cosine squared t plus negative e to the power of negative t squared. And we know that sine squared t plus cosine squared t equals 1. So we can just replace those two terms. And after squaring negative e to the power of negative t, we're going to get e to the power of negative 2t. So all in all, we have the magnitude of the seed's velocity, which is just the square root of e to the power of negative 2t plus 1. Now that we have this, we can move on to actually finding the components of the seed's acceleration. Let's start with tangential. So with tangential, we're going to need to find the dot product between velocity and acceleration. We have the dot product here. Sine t, cosine t, negative e to the power of negative t, dot product cosine t, negative sine t, e to the power of negative t. Our dot product will end up being sine t times cosine t plus negative sine t times cosine t plus negative e to the power of negative t times e to the power of negative t. You'll notice that the first two terms, sine t times cosine t and negative sine t times cosine t, are just going to cancel each other out. So we're just left with a negative e to the power of negative 2t from the last term. And once again, we've already gotten the magnitude of our velocity function, so we can just put that in there. Square root of e to the power of negative 2t plus 1. All in all, we have the tangential component being negative e to the power of negative 2t all over the square root of e to the power of negative 2t plus 1. All that's left to do now is look for the normal component, which is going to be a lot more, well, calculation intensive. First of all, we're going to need to find the magnitude of the cross product. You can verify yourself, but the cross product of the two vectors is going to be cosine t minus sine t times e to the power of negative t, negative cosine t plus sine t times e negative t, and then negative cosine squared t plus sine squared t. We're going to need to find the magnitude of this, which means we need to take the square root of every term squared added to each other. I just want to get out of the way first that cosine squared t plus sine squared t once again equals 1. So our third term is just going to be negative 1 squared. Now moving on to the other terms, we have cosine t minus sine t times e to the power of negative t squared, and we have negative cosine t plus sine t times e to the power of negative t squared. Now squaring both of these, we're going to get something like cosine t minus sine t squared times e to the power of negative 2t plus cosine t plus sine t squared times e to the power of negative 2t. And what do we have? We can factor out the e to the power of negative 2t here. And we end up with cosine t minus sine t squared plus cosine t plus sine t squared, all times e to the power of negative 2t. And then we have the plus 1 at the end from the last term, and that's all that's in the square root. What are we going to have here? We can square the stuff inside the e to the power of negative 2t term in order to get us cosine squared t minus 2 times sine t times cosine t plus sine squared t. And then for our second, we have cosine squared t plus 2 sine t times cosine t plus sine squared t. We get something along the lines of 2 cosine squared t plus 2 sine squared t plus 2 sine t cosine t minus 2 sine t cosine t. And we can just cancel out the sine t, cosine t terms because they're going to just sum each other out. So we're left with 2 cosine squared t plus 2 sine squared t. And once again, cosine squared t plus sine squared t is going to equal 1. And because we have 2 of those, we just simply multiply the e to the power of negative 2t by 2. Which leaves us with the square root of 2 times e to the negative 2t plus 1 all over the square root of e to the negative 2t plus 1, which, as we've established before, is the magnitude of our velocity component. And that's all the 3 practice problems solved. Thank you for watching, and please, if you want to review any of the other topics, please do feel free to watch all the other videos, or maybe even rewatch. Thank you for watching this tutorial video.